This tutorial illustrates some postulates of quantum mechanics about the outcome of measurement of position or energy of a particle in a potential energy well. We consider a one-dimensional model where a particle is trapped between two infinite potential energy barriers for x smaller than 0 or x larger than 1. The potential energy is assumed to be infinite, but inside the trap, the potential energy is constant and set equal to 0. The particle, therefore, has only kinetic energy. By choosing Cn and by varying the quantum number n, which takes positive values equal to 1 or larger than 1, we can see the different acceptable eigenfunction of the time-independent Schrödinger equation, which is written here for the case where the particle has only kinetic energy. The eigenfunctions are sign functions. In fact, they correspond to the de Broglie waves for a free particle which has only kinetic energy, but the sign functions are the only ones which are 0 for x equals 0 or x equals 1, so they are 0 at the boundary of the trap. For n equals 1, we have the ground state, n equals 2 first excited states, and we see the only acceptable wave function for this model. Now, by choosing the square modulus of the wave function, the figure gives the density probability of localizing the particle. By varying xmin and xmax, we define a domain, and the probability of localizing the particle in this range is given by the integral of the square modulus of the wave function over this interval. The result is given above the graph. For instance, for the ground state with n equals 1, the probability of localizing the particle in this small interval with a width 0.1, for example, so it is given by this gray area. The probability of localizing the particle is very, very small. Now, we may move the interval at the middle of the trap by keeping the same width, which is here 0.1. So I try to get the same width, which is 0.1, okay. And now the probability of localizing the particle in this interval is very higher. This result is very different from the prediction of classical mechanics, which should give the same probability regardless the position of this interval. We will now discuss the outcome of the measurement of the energy of the particle. When it is in one of the eigenstates of the time-independent Schrödinger equation, that is, if the particle is described by one of the acceptable sign functions which vanish at the boundaries of the trap, then the outcome of the measurement will give the eigenvalue with a probability of 1. The eigenvalue take this expression. They depend on the quantum number n, the mass of the particle, and the width of the trap. For instance, when the particle is in the ground state, the measurement of the energy will give the lowest possible value of the kinetic energy. And it is a non-classical result, since classically the kinetic energy of a particle may vanish. When the particle is in the first excited state, the outcome will give the second eigenvalue, so the kinetic energy is 4 times greater. If it is in level n equal 3, the energy will be 9 times higher. So, for every eigenstate, which are also called stationary states, the measurement of the energy gives the eigenenergy with a probability of 1. Now we will illustrate how we could prepare a non-stationary state. I take back the model of an infinite well with a width of 1 and a particular eigenstate represented in black. By modifying the quantum number j, one may choose different eigenstates of the small well. I take back, for example, the ground state. At a given time, the width of the well is suddenly multiplied by a factor n, and one may choose 2, 3, or 4. For instance, I take 2, like this, and I choose the ground state. At that moment, the function is no more an eigenstate of the new well. The eigenstates are the acceptable sign function for the large well, and they are delocalized over the whole region. They are represented in red. At the time the well is enlarged, the black function is a nice example of a superposed state or a non-stationary state. It may be expressed as a linear combination of all the eigenfunctions of the new system. Here they are represented in red. The coefficients of this linear combination are the overlap integral or the dot product. It is the integral of the product of the studied functions, so the black function, and all the eigenfunctions of the system, so here the red function. The value of the coefficient are represented on the left, and one sees that they may be positive, negative, or null. With the button Nmax, one can check the convergence of this linear combination. Nmax represents the number of terms which are included in this sum. For example, with n equal to 1, it is very bad. There is no equality between the two expressions. When we include 2 terms, it is better, better and better and better, and it is expected from the value of the coefficient which are represented here that the sum converge with about 10 or 15 terms. In fact, this sum contains less than 15 terms, since a lot of coefficients are equal to 0. Let us now come back to the postulates about measurement. Just at the time after the enlargement of the width, the wave function is unchanged, so the probability of localizing the particle remains unchanged at that time. On the contrary, the outcome of measurement of the energy is completely different from the previous stationary case. For this new superposed state in the new well, the outcome of measurement of energy will be one of the eigenvalue of the new well. The eigenvalue take the usual expression, but we have to use the new width of the well. And the probability to get any eigenvalue is given by the square modulus of the coefficient of the linear combination. On the left, here we recall the coefficient of the linear combination describing the superposed state, and on the right we have the square modulus, so the probability to get any eigenvalue. In this example, we mainly get E1, E2, E3, and here we have the average value of the energy, and here the standard deviation of the distribution of the outcome of measurement. By varying the J quantum number, we can analyze another situation, for example, for the second excited state n equal 3, we get a different distribution of the probability to get any eigenvalue for the outcome of measurement of the energy. Be careful that we have considered only the time t, and in the next